Hello friends, this is video number 2 of a series where we go through the book Weinberg's Lectures on Quantum Mechanics by one of the great theoretical physicists of the 20th century, Steven Weinberg. Today we present part 2 of chapter 3. Recall that we will not be reading the book in order, as explained in the last video, due to pedagogical reasons. We have a lot to cover today, so let's begin. We continue with our discussion of quantum kinematics, which is how we describe the states of quantum systems. In the last video, the notion that quantum states are vectors in a Hilbert space is introduced, and these vectors are denoted by cats in Dirac's bracket notation, which can be expressed in terms of elements of a vector basis. These elements are eigenvectors of some observable A, which can be represented by a Hermitian operator. Elements of this basis represents the outcomes we get when measuring this observable on a system, which is in some initial state psi. The components alphas represent the probability amplitudes of finding the system in these outcomes. The probability itself is given by the absolute square of the amplitude. In the last video, we have dealt exclusively with discrete states with measurement outcomes that could be labeled by a discrete index. When the total number of outcomes, n, is finite, we say that the system lives in a finite-dimensional Hilbert space. In principle, n could also be infinity, which means the number of basis elements is infinite, but still discrete, and the results we have derived in the last video will typically hold without any modifications. When n is infinite, the system is said to live in an infinite-dimensional Hilbert space. There is another type of Hilbert space belonging to this category, but with basis elements that formed a continuum, and must be labeled by continuous variables. This is where the continuum states live, which is what we will talk about next. As a first example, let's look at the state of a particle with definite positions along the x-axis. We shall start with an infinite lattice, where the particle could only be in discrete positions at lattice points, then approach the continuum by taking the appropriate limits. The spacing delta x between adjacent positions is assumed to be finite. If the particle is in position xi, then it is in a state represented by cat xi. This is the discrete position state. Each position is associated with the corresponding position state. We then take the continuum limit by letting delta x goes to 0. As a result, the lattice points cover the entire x-axis, and we replace the discrete position label by the continuous position variable x, and the corresponding position state by cat x. Cat x is a continuum state that represents the particle being in a definite position x on the x-axis. We now make a comparison between the discrete and continuum vector spaces, and see how objects in the continuum can be derived from those in the discrete space by taking a continuum limit. A set of discrete basis states lived on the lattice along the x-axis. The particular bases we have chosen are states of definite positions at the lattice points. The continuum counterpart is given by: in the discrete space, an arbitrary state that lives on the lattice is given by the following, which is a state that may not be in a definite position, but when we try to measure the position of the particle, it could be found at some position I, with probability given by the absolute square of the corresponding amplitude psi I. We claim that when the continuum limit is taken, this corresponding continuum state is obtained. The amplitude psi x is what is known as the wave function in position space. To derive the continuum state, we first take the discrete state and insert the lattice spacing delta x in the numerator and denominator of the summand. One copy of delta x is grouped with the sum, while two copies of the square root are grouped with the amplitude and the discrete position state respectively. In the continuum limit, delta x goes to 0, while the sum becomes an integral, which is just what you get from taking the limit of a Riemann sum. The other two terms become the wave function and the position state in the continuum. The discrete position label I is also replaced by the continuous variable x. Therefore, the continuum state is obtained in the limit, as stated previously. This trick, in which we insert delta x and replace the sum with an integral to get continuous quantities from their discrete versions, is one that will be used very often, so please take note. Let's take a closer look at the newly defined position state. The discrete version of this state satisfies the autonormality conditions. We now wish to know the normalization conditions for the continuum position state. Let cat x be the state that is approached by the discrete state xi in the continuum limit, and cat x prime by the state xj. The inner product of x and x prime is given by the following. We claim that this is the famous Dirac's delta function, invented by Paul Dirac, who was one of the founding fathers of quantum mechanics, and who also invented the bra and cat formalism. We can think of Dirac's delta function as the generalization of the Kronecker's delta to continuous variables. This function is defined with the following properties. Taking x as the variable and x prime as a constant, the delta function is infinite where x is equal to x prime, and 0 everywhere else. Let's look at the limit function. We can see that when I is equal to j, the value of this function, 1 over delta x, also approaches infinity, as delta x approaches 0. And where I is not equal to j, it is also 0, similar to Dirac's delta function. Remember that I is mapped into x and j into x prime. This shows that the function approaches the delta function in the limit. Let's look at another defining property of the delta function. The integral of the delta function with an arbitrary function f picks out the value of f at x prime. Note that x prime is a constant position under the integral. This property holds because the delta function has 0 support everywhere except at x prime. More explicitly, let's replace the integral by its discrete version. Delta x from the sum cancels with that from the delta function, and the remaining Kronecker delta picks out f at point xj. But recall that xj is just x prime. Therefore, we get the stated identity. If f is set to 1, we immediately obtain the special case, which states that Dirac's delta function is normalized to 1 when integrated over the entire x-axis. Both of these are important properties of the delta function. In fact, the delta function is actually defined by how it acts under an integral. Here are some common identities about the delta function. The delta function is symmetric in its argument. This can be seen from the Kronecker's delta in its definition, which is symmetric in its indices. Another useful function is delta of fx. Intuitively, it imposes the constraint fx equals to 0 when inserted into an integral. Let's see how it works. Gx here is an arbitrary function. Again, it will prove useful to substitute this integral with its discrete version. Note that delta f in the denominator of the delta function is the measure of f if f is treated as an integration variable. Therefore it is positive, hence the absolute value is taken. This must be so, since f is the argument of the delta function. The Kronecker's delta imposes the constraint fx equals to 0 and picks out all the roots of this equation from under the sum. Therefore, we get the following, where the sum is now just over the roots, and the Kronecker's delta just evaluates to 1, since the constraint equation is satisfied at all these points. We can see that the term in the yellow box is just the inverse of the derivative of f, evaluated at xr after the limit is taken. And so we obtain the result of the integral. From this equation, one can see that delta fx can be replaced by the following expression. This works because the delta function pulls out all the roots from under the integral over x and picks out the values of function g evaluated at these points. Take note of this identity as we shall use it often. As a final note on Dirac's delta function, we introduce the following integral representation. The integration variable k is the wave number of the one-dimensional plane wave described by the exponential function. To prove this identity, we shall use the old trick of proving first the discrete version, then take the continuum limit to get the final result. Here's the discrete version of the identity regarding the Kronecker's delta that we are going to prove first. The indices L and M run from 1 to n in integer steps. Let's look at the right-hand side of this equation and see how it could be equal to the left-hand side. We make a change of summation variable to n prime, such that the sum now runs from 0 to n minus 1, and also pull out a phase factor. This will make the sum a simple geometric series. Let's look at the expression in the yellow box. When L is equal to m, each term in the sum becomes 1. And the sum just evaluates to n, because there are n terms. What happens when L is not equal to m? To answer that, let's sum the geometric series in the yellow box, and we get the standard result, where r is given by the following. Notice that r is not equal to 1 when L and m are not equal, and also when the magnitude of their differences is less than n. This last statement is automatically true when L and m range from 1 to n, which is precisely the domain of these indices. This means the denominator of the sum is non-zero. On the other hand, r to the power of n is equal to 1, which implies that the numerator of the sum is equal to 0. So we can conclude that the sum is equal to 0 if L and m are not equal. Therefore, we get n times delta Lm for the expression in the yellow box. Due to the Kronecker's delta, the phase factor outside the sum is just 1. Substituting this result back into the original expression, and cancelling the factors of n, We show that the sum is equal to the Kronecker's delta, thus the discrete identity is proven. By a change of summation variable, the limits of the sum can be made more symmetric. Again, we will be able to pull out a constant phase factor that can effectively be replaced by 1, since it is multiplied by a term that is proportional to delta Lm. Let's put our results in order. We arrived at an expression of the Kronecker's delta in terms of the summation of phases over symmetric limits. This will be the starting point from which we take the continuum limit to obtain the corresponding equation for Dirac's delta function. Recall that the delta function is related to the Kronecker's delta by the following relation, where delta x is the minimum lattice spacing. Using the identity for the Kronecker's delta in the yellow box, we get, once again, the discrete positions indexed by L and M can be identified with x and x prime. L is the total length of the lattice given by the total number of lattice points n multiplied by delta x. Substituting this into our equation, we have We then identify 2 pi n over L as the wave number kn. Note that n ranges between these limits and is an integer. It is implicitly assumed that capital N is even. Its exact value is not so important since eventually we let it go to infinity in the continuum limit. Because n is an integer, its minimum increment is 1. This implies that the corresponding increment in wave number is 2 pi over L. Using this relation, we can write the summation as bringing in a 2 pi in the numerator and denominator to give the following, which is a sum in increments of k. Now we take the continuum limit where delta x goes to 0 and n goes to infinity in such a way that the lattice length L becomes infinite. This also implies that the finite delta k becomes infinitesimal and the wave number kn becomes a continuous variable k. Substituting these two results back into our equation, we obtain the following, which proves the identity. This equation lies at the heart of Fourier transformations, and therefore appears in many areas of physics. We shall shortly use these equations to relate position states with momentum states in quantum mechanics, so take a moment to write them down if they are not familiar to you. After this long interlude about the delta function, let's get back to our discussion of continuum position states. We have just worked out that these states normalize to the delta function when they are defined like so. This definition comes from the previous result where we derived the general continuum state cat psi expressed in the basis of position states. We now look at the properties of the wave function of this state, psi x, which as you would recall is defined by the following. This is a function derived by taking a limit on its discrete counterpart. We can use the discrete amplitude psi I to tell us what the wave function psi x means. Recall that the absolute value of psi I tells us the probability that the particle will be found at the lattice point xi. From the definition of the wave function, this probability is just equal to the absolute square of psi x multiplied by the small interval delta x around the point xi. In the continuum limit, when delta x goes to 0, the total probability is distributed continuously across the x-axis. The probability of finding the particle at any point xi obviously goes to 0, as can be seen from this expression. In order to get a finite probability, we need to sum over some finite interval, for example a and b. Which in the continuum limit just means integrating the absolute square of psi x over this interval. Therefore, the absolute square of the wave function in position basis is a probability distribution over position space. This function, when integrated over the entire position space, which is the x-axis in our example, must give 1 if it is a probability distribution. This is the normalization condition that has to be satisfied by all probability distributions, and closely mirrors the result from the discrete case. Let's look at another way of representing this normalization condition. Starting with the state vector in position basis. Using the standard prescription for Hermitian conjugation, we also have bra psi. Taking the inner product to get the square norm, we get, which could be evaluated using the orthonormality of the position states. We then arrived at the integral of the absolute square of psi x over all positions, which must be equal to 1. Thus we have shown that the inner product of a state with itself must be equal to the sum of probabilities, a result we have proven in the previous video for discrete states. Therefore, this relation holds for both the discrete and continuum cases. This equation is usually what comes to mind when one says that the state is normalized. At this point, it seems pretty clear that we can obtain identities in the continuum from their counterparts in the discrete case, simply by some rules of substitution. We now give a summary of these rules. We start with an object that lives in discrete space and expand it in terms of some vector basis in Hilbert space. Assume that this basis satisfies the orthonormality conditions. This object could be a state vector or an operator. The point is that both of these are basis-independent objects. For example, the state vector could be represented in many different bases, each associated with a different set of components. Putting them together, we get the same vector which encodes the same physical information. The same goes for an operator, as it is just a prescription to map a vector onto another vector, and therefore is also basis independent. Next, we use the usual trick of inserting into the sum a small change in variable, here generically represented by delta xi. Xi is a continuous variable, which is mapped from the discrete index I as the continuum limit is taken when delta goes to 0. Let's further expand the term in a square bracket, which may contain a vector element of the discrete basis. The delta in the denominator can then be divided equally among the two terms. The vector thus gets a factor of inverse square root delta to form the state xi, which is an element of the continuum basis. The key point is that the discrete basis vector must always be paired with a square root delta, such that it forms a continuum basis vector that normalizes to a delta function. This is important because a delta function is well defined under an integral, which we must evaluate when taking inner products between states in the continuum. The other term that comes together with the vector then absorbs the remaining inverse square root delta. This term could itself be a vector or just a number. Its absolute square must then be a distribution, like the probability distribution we have just talked about, or a delta function, something that gives a finite result under an integral. Finally, we replace the sum by an integral in the continuum limit. Note that all objects under the integral are now continuum objects, which consist of continuum basis vectors and continuous variables, which used to be discrete coefficients. This integral is still basically a vector basis expansion, with the basis elements now labeled by the variable xi. Here we collect all the rules for converting discrete objects into their continuum versions. These rules dictate the relations between the discrete and continuum regarding variable, state, inner product, and basis expansion. We now look at a few examples of applying the conversion rules. This will allow us to translate all the operators in Hilbert space derived in the last video to represent discrete observables to their continuous versions. Let's start with the most useful operator, the identity operator. For the discrete case, the cat-bra representation of the identity operator is given by the following, where we have chosen the discrete position states as a basis. Recall that this is the generic form we have derived in the last video, in which the sum runs over the entire basis. This representation of the identity is adequate for the discrete degrees of freedom, but unsuitable for continuous states. A more suitable representation would be this, where the conversion rules are employed, replacing the sum with integration over continuous positions and the discrete basis for continuous one. We shall refer to this expression as the resolution of identity in position basis. Note that from here on, we will always refer to position as a continuous variable. Now we check if this operator is really the identity for continuous states. Let's apply it to an arbitrary state psi. Using the autonormality condition for position states, a delta function is introduced into the integral. After integrating out x prime, we get. Thus we get back the same state just as expected. Our next example is an operator that is very similar to the identity operator. It is the projection operator, or the projector. We have talked about this extensively in the last video for discrete states. Basically, a projector projects out states from a chosen subspace in Hilbert space, while eliminating states that are outside this subspace. Check out Lecture 1 for more details. Here we will show how the previous results translate to the continuum states. Let's look at a projector that projects into the subspace of position states that lived on an interval along the x-axis. We denote this interval by AB. The discrete version of the projector is given by the following, in which we summed over all projectors associated with every position within the interval AB. This is translated to the continuum by replacing the sum by an integral, while switching to continuum position states. Let's apply this operator to an arbitrary continuum state psi. In general, the wave function of this state can be distributed over the entire x-axis. The projector introduces a delta function into the integral, which selects only points within the interval AB. Upon integrating out x prime, we obtain the resulting state, which is the original state with regions outside of AB eliminated, while leaving the part within AB unchanged. Essentially, the portion of the state within AB is projected out just as expected. Now we see why this operator is called a projector. Let's look at another property of a projector. Suppose there is another projector that projects out a different interval CD. What happens when we apply these two together? Once again, the overlap of the projectors gives rise to a delta function. This delta function is only non-zero in the overlapping domain of intervals AB and CD, where x is equal to x prime. This results in an integral over the intersection of the two intervals, denoted by D. Hence we obtain the property that the composition of two projectors gives another projector into their intersection. The next example is the position operator. For discrete states, this is given by the full rationale of why such an operator represents the position observable is discussed in Lecture 1. Here, we merely note that it captures all the properties associated with the position observable, namely, the full spectrum of states with definite positions and their corresponding measured values. This cat-bra representation tells us that this operator acts on the position state xi and gives back the same state multiplied by its eigenvalue. Thus, the eigenvector equation is satisfied. The key identity we have used is again the orthonormality of the position states. This position operator is naturally extended to continuum states as the following, which also satisfies the eigenvector equation now with continuum position states. The orthonormality conditions are just replaced by the continuum form. There may be observables that are functions of position. These are represented in this way. For discrete states, which maps into the continuum in a straightforward manner. This automatically satisfies the eigenvector equation. The function of the position operator can be used to describe a potential acting on a particle which is dependent on its position. We have said quite a bit about observables based on the position of a particle. It's now time to describe its motion. The most elementary variable that describes a particle's motion is its momentum. The momentum variable goes with a corresponding position that runs along the same coordinate axis. Together, they form a canonical conjugate pair under the framework of Hamiltonian mechanics. Recall that we have assumed only one spatial dimension, where a particle moves and is located along the x-axis. Later, we will generalize our results to higher dimensions. This is in fact quite straightforward. Since momentum is a continuous observable, we could immediately write down the cat-bra representation of its operator, like so, where P is its eigenvalue that runs along the entire real line. The momentum eigenbases are continuum states that normalize to a delta function. They represent states of a particle with definite momenta. In this form, the momentum operator is explicitly Hermitian. Since the momentum states form a complete basis, the identity operator could be resolved in this basis. At this point, our mathematical description of momentum seems to be identical to position. Just replace x with p, and you get all the same equations. Therefore, to take a non-trivial step forward, we would need to add more physical content. Namely, what is the relation between p and x? Remember where this inner product comes from. Which is state p expressed in the position basis. Thus, the inner product xp is the wave function of the momentum state in x basis, or the position space. It describes how the amplitude of the momentum state is distributed spatially. Note that the term amplitude is often used interchangeably with wave function. What then should this function be? To answer this question, we shall apply the principle of wave-particle duality, which states that all matter can be described by both a wave and a particle, as postulated by Louis de Broglie. In particular, the momentum wave function will be identified with de Broglie's matter waves. The idea of wave-particle duality comes from investigations into the nature of light, whether light is a wave or a particle. In classical physics, light is described as an electromagnetic wave, which is derived from Maxwell's equations of electrodynamics. But at the turn of the 20th century, the particle nature of light began to emerge from the study of blackbody radiation by Planck and its interpretation as light quanta by Einstein. These are discrete packets of energy and momenta, which can be described by massless particles, the particles of light. The synthesis of these two results allowed Einstein to establish the wave-particle duality of light. Let's see what this means. If light is a massless particle, then it will have to satisfy Einstein's equation for the relativistic particle. The energy each particle carries must be given by, as implied by Planck's radiation law. If light is a wave, then its frequency is related to its wave number, as in a plane wave. Note that c is the speed of light, and omega its angular frequency. On the particle side, we can express the momentum as the following, while on the wave side, combining these two equations. We get an equation relating the momentum of a particle to its wave number. This was then postulated to describe all particles, including massive particles like the electron, by Louis de Broglie in his PhD thesis building on the work of Einstein. Thus, the wave-particle duality is promoted to a universal principle. Note that the energy of a free particle is still related to its momentum by Einstein's equation. Setting m equals 0 gives back the same equations previously established for light. Therefore, this generalization is consistent. De Broglie's formula suggests that we should describe the wave function of a particle having a definite momentum by a plane wave. The next step is to find the constant of proportionality for this function, which is actually quite simple since we know the momentum states normalize to a delta function. Inserting the identity operator resolved in the position basis allows us to relate this to the momentum wave function. The delta function can also be expressed in its integral representation, which we have derived earlier. Compare this to the left-hand side. We get the exact expression for the wave function of the momentum state and its complex conjugate. We find the prefactor of the wave function to be 1 over square root 2 pi h bar. Of course, if you like, you could make the dependence on p in the exponent explicit, but I'd rather not have too many h bars floating around. But if you do worry about the h bars, let me show you quickly where the h bar in the denominator comes from. Let's go back to the delta function for p. Using the rule where constants could be moved out from within the argument of the delta function, we can relate this to the delta function for k. This can then be expressed in its integral representation. Notice that the argument of the exponential function is dimensionless. This is necessary to ensure dimensional consistency. Therefore, we always choose an integration variable with the right dimensions, which in this case is position, to cancel the inverse length dimension of k. In such a way, we end up with a h-bar in the denominator. It is important to note that this is the point where the constant h-bar is introduced into the formalism of quantum mechanics. Just to remind you, h-bar is the reduced Planck constant with a factor of 2 pi in its denominator. In this way, we incorporate the principle of wave-particle duality into the theory. If we can see bracket xp as the wave function of state p in the x basis, what can we say about px? Let's attach this component back to the matching momentum basis. In this form, it is obvious that bracket px can be seen as the wave function of state x in the p basis. Compared with the previous function, we see that in the first, the momentum p labels the state itself, while x labels the components in position basis. And in the second, x labels the state while p labels its components in the momentum basis. These two are just a complex conjugate of each other. Let's take a closer look at the relation between position and momentum space. Take an arbitrary state psi and express it in the position basis. Then take the same state and do the same thing with the momentum basis. The components associated with the first basis is called the wave function of psi in position space, while those in the second basis, the wave function of the same state but in momentum space. We denote the first function as psi of x and the second as tilde psi of p. How are the two functions related? We can easily find out by again using the trick of inserting the identity operator in the right places. Therefore, the momentum space wave function of psi is just a Fourier transformation of its position counterpart. As an example, let's use this formula to derive the famous Heisenberg Uncertainty relation. We shall look at an important class of wave functions known as the Gaussians. A state described by a Gaussian wave function has a probability distribution given by a Gaussian function. In this example, we start with a distribution in position space. Let's find the normalizing factor of this distribution. To do this, we need to evaluate a Gaussian integral, where a is a constant. The solution is given by. This is a standard formula, and you can find the proof on Wikipedia. Briefly speaking, to solve this, just convert this to a two-dimensional integral, which is easily solved by a change of variables to polar coordinates, then take a square root at the end. This identity is very important in quantum mechanics, and therefore would be very convenient to memorize. A more general form of the Gaussian integral is given by this, which just includes an additional linear term in the exponent. The result is an exponential in addition to the square root term. This integral is solved by completing the square in the exponent and using the previous result. Evaluating the integral, and we get a normalized Gaussian distribution. Assuming that the wave function psi x is real, it is just obtained by taking the square root of the probability distribution. Thus, we have the position space wave function of state psi that corresponds to a normalized Gaussian distribution. A question we may ask is, what is the significance of the constant A? To find out, let's evaluate some statistical quantities of the distribution and see how they are related to A. We put the distribution here for easy reference. Let's calculate the average position. Since the distribution is an even function and x is odd, this integral is 0. Thus the average position is 0. Next, let's calculate the average of x squared. Since x squared is also even, this integral is non-zero. Leaving the constants aside and just focusing on the integral, we can bring down the x squared by taking the derivative of a and cancelling the minus sign. Tricks like this are called differentiating under the integral and are pretty handy. The term in the yellow box is just a Gaussian integral which is readily solved. Taking the derivative of this gives, which solves the integral. Let's substitute this back to the main expression. And we get this simple result for the average of x squared. This happens to be the square of the spread in position, since the average position is 0. The spread is a measure of the average width of a probability distribution. Let's rearrange this equation. We see that A is related to the inverse of the square of position spread. This has the dimension of inverse length square, which nicely balances the x square in the exponent. The prefactor of psi x also works out fine, since it is of dimension the negative square root of length that comes from the position state x, which has the same dimension, since it is equivalent to the square root of a delta function. So our calculations are consistent with dimensional analysis. Given that we have a Gaussian wave function in position space, what is the corresponding wave function in momentum space? This is given by the following Fourier transformation. Let's substitute our Gaussian wave function. Setting aside the constant factors for a moment and focusing on the Gaussian integral, we find that this is the standard integral stated earlier with an extra linear factor in the exponent. Brackets of matching colors in this identity represent the same constants. By substituting the constants of our integral into the appropriate slots, we get the following result. Which is then inserted back into the main expression. Now consolidate all the constant factors into a single term. This can be rewritten to match the standard Gaussian form seen above. The wave number k in the exponent is then written in terms of momentum p using de Broglie's formula. Thus we obtain the wave function of state psi in momentum space. Note that this wave function is also a normalized Gaussian, as it can be written in the standard form. This is a general result. The Fourier transform of a Gaussian always results in another Gaussian. Let's identify the spread of the momentum wave function like we did for position. Notice that the constant a in this equation is the same one that we have found earlier, which is related to the position spread. This implies that delta p and delta x are not independent. More explicitly, replace a with its dependence on delta x. Then do a little rearranging. And we get a constraint on the spread of x and p. This is a special case of the more general inequality known as the Heisenberg Uncertainty relation. This says that the position and momentum of a particle cannot be simultaneously known to arbitrary precision. We shall prove the general form of the uncertainty relation using a different method in a minute. The Gaussian wave functions can be seen as minimum uncertainty states in position and momentum space because they saturate the minimum uncertainty relation. Next, let's see how the momentum operator acts on continuum states. Its action on the momentum state is simple and is just given by the eigenvector equation. How about the position state? To find out, we can apply the identity operator in the momentum basis. This is simplified by using the eigenvector equation, which allows us to replace the momentum operator by its eigenvalues. Notice that the term in the yellow box can be replaced by a derivative of bracket px. This is apparent from the expression of px derived earlier. Since this is an x derivative, it acts directly on the position ket, which depends on x. The derivative of a ket works exactly the same way in calculus by taking the following limit. Note that since the difference of two vectors is also a vector, the result is simply another ket. The same rule applies to the derivative of the conjugated state as well. Next, we reassemble the integral of the ket bras of p into their respective operators. Therefore, we obtain the result that p acting on ket x is equal to taking a x derivative. Taking the Hermitian conjugation of this equation, we get the result for bra x. This is the form that is more commonly applied. For instance, when we derive the action of operator p on the wave function of a state psi, This equation tells us that it is equivalent to taking a derivative on psi in position space. Here's how we see it. The left-hand side of this equation reads px on psi and is then projected into position space. This is equal to the right-hand side, which is the x derivative on the components of psi in x basis, which is the wave function of psi in position space. In other words, since psi is arbitrary, the representation of operator p in position space is given by the derivative. Conversely, how does the position operator act on the momentum state? This is actually very similar to the previous derivation. Start by expressing operator x in the position basis. Once again, we can rewrite the term in the yellow box as a derivative, but this time a p derivative, as can be seen from the expression for bracket xp. Proceeding as before. We obtain the action of operator x on state p. This is almost identical with the previous result, except we are taking momentum derivative on the momentum state, and there is an extra minus sign from complex conjugation. This highlights the complementary relation between position and momentum. Once again, the Hermitian conjugation is taken. This result now allows us to derive the representation of position operator in momentum space. Now let's look at the representation of x and p in position space and work out some relations that are basis independent. Recall why the position operator is represented by its eigenvalues in position space. Starting with the eigenvector equation for bra x, we see that when the result of x acting on an arbitrary state psi is projected into position basis, what we get is just psi x multiplied by x. Let's look at the commutation relation between x and p. Recall that the commutator between two operators, a and b, is defined by. We have examined the properties of this object extensively in Lecture 1. Check it out if you need a review. Now apply this to x and p. After expanding out the commutator, we notice that the second term can be further evaluated using the product rule of derivative x. This leads to the cancellation between the first and the last term. Since psi x is an arbitrary function, the following relation between the two operators remains. This says that the commutator between position and momentum along the same axis is not zero, but equal to the number IH bar. The implication being that there cannot be a simultaneous eigenstate of position and momentum. That is, the two variables are complementary. This is the point where we extend our discussion to higher spatial dimensions. For 3D space, the y and z operators must also be included. It is convenient to label the various components by an index. This makes it easy to generalize to arbitrary dimensions. But for now, we will stick with 3D. Empirical evidence suggests that all components of position can be simultaneously observed to the same precision. Therefore, the operators representing them should all commute with each other. Consequently, the position state can be fully specified only by adding two more eigenvalues corresponding to the extra components. We gather all these components into a position vector which labels the position eigenstate. The same arguments can be made for the components of the momentum operator and its eigenstates. These results can be combined with the commutation relation between position and momentum derived earlier. Which generalize naturally to 3 dimensions. The Kronecker's delta on the right-hand side of this equation suggests that different components of position and momentum commute, while components along the same axis do not. Taken together, the only commutators that are non-zero are those between the canonical conjugated pair of position and momentum. Therefore, these are commonly referred to as canonical commutation relations. Consequently, they can be regarded as quantization conditions to promote a classical system to a quantum mechanical one. Because this represents a departure from classical mechanics where all variables commute and can be simultaneously observed. Now, let's work out another commutator that will be quite nifty in calculations, which is the commutator of x with an arbitrary function of x and p's. We claim that any function f of position and momentum operators can be written in the form with position to the left and momentum to the right. This can be seen just from the commutator between x and p. If x and p are of the same direction and do not commute, we can still move x to the left of p by just adding another term minus I h bar, which is just a number that commutes with all operators. In this way, we can rearrange any combinations of operators such that x is to the left and p is to the right. As we shall see, f written in this form will make our calculations much simpler. Here we make use of the product rule of commutators derived in Lecture 1. This product rule is actually much more general, and is in fact closely related to the product rule of derivatives, as can be seen in the representation in the yellow box. The key point here is to preserve the relative ordering of the A operators. We shall use this representation almost right away. Going back to our calculation. We see that the first commutator, after applying the product rule, is 0, as components of the position operator do not commute with each other. As for the second commutator between x and the functions hi that depend only on the momentum operators, we can apply the product rule again, which can be easily evaluated using the xp commutators. Since gi is purely a function of x, we can pull out the p derivative. And the expression in the yellow box is just a function f. This gives a nice result for the commutator between xi and the arbitrary function f. We emphasize again that the p derivative must be applied in a way that respects the relative ordering of operators within f. A very similar identity holds for the commutator of f with pi. The proof is practically identical with what we have just gone through, and made use of only the basic commutators at the top as well as the xp representation of f. Together, these equations allow us to evaluate any commutators of functions of x and p quite easily. Now we will present a derivation of Heisenberg's uncertainty relations under general conditions. That is, without assuming the wave functions to be of any particular form, like the Gaussian function. But first, we will need to derive an inequality that is quite important in quantum mechanics, the Schwarz Inequality. It has the following form, where psi and phi are any two vectors in a Hilbert space. We will need this to prove the uncertainty relation. One can gain some intuition about how this relation comes about by looking at the special case of real vectors. The inner product between two real vectors, v and w, is just the usual dot product, which is given by the projection as seen below. The Schwarz inequality then simply states that the magnitude of a cosine must be less than or equals to 1. This is an obvious fact. With this understanding, we can now consider the general case of complex vectors on a Hilbert space. We begin with the general statement that any vector psi can be expressed as a linear combination of some vector phi and a vector that is orthogonal to phi. It is assumed that phi and phi perpendicular are both normalized, and so is psi, which means the absolute squares of alpha and beta sum to 1. Given this representation of psi, the magnitude of the inner product between phi and psi is simply the magnitude of alpha, which must be less than or equal to 1, as constrained by the normalization condition. Since both phi and psi are normalized, this is also equal to the product of their magnitudes. And we have basically arrived at the Schwarz inequality. The only step left is to show that this will still hold if we do not assume the vectors to be normalized. This can be seen this way. Any unnormalized vector, psi, can be normalized to a parallel vector, psi tilde, with a normalizing factor, and similarly for phi. Here we notice that the normalizing factors for both sides of the Schwarz inequality are actually equal and so cancel out. Therefore, the inequality also holds for unnormalized vectors. This completes our proof. Now finally, we are ready to prove the famous uncertainty relation. Suppose we have two Hermitian operators that represent the observables we intend to measure of an arbitrary state psi. It is important to note that psi is normalized. As usual, all average values of operators are given by the bracket of psi. The square of the standard deviation of some observable A is also an average value. This standard deviation would be the measure of uncertainty. We can write this in a more compact way by introducing another Hermitian operator, A tilde, which measures the deviation from the average value of A. We define the resulting state of A tilde acting on psi as the following. Therefore, the square of the standard deviation of A can be written as the inner product of the vector A tilde with itself. The uncertainty in B can be written in a similar way with the introduction of B tilde. Using this compact notation, the product of the standard deviation squared of operators A and B is given by the following. It is at this point that the Schwarz inequality can be applied. Here we further notice that the absolute square of the inner product of the vectors a and b tilde must be greater or equal to the square of the imaginary part of the same inner product. Let's expand this imaginary part in terms of the bracket ab tilde as well as its complex conjugate ba tilde. By using the definitions of a tilde and b tilde, both brackets can be expressed as below. Remember that all these brackets are taken in terms of psi. Looking at the expression in the yellow box, we notice that it is equal to the difference between two terms of opposite ordering. Thus we can immediately conclude that terms linear in operators, or are just purely numbers, must cancel out as they are not sensitive to operator ordering, leaving only terms that are quadratic in operators, which is found to be the commutator between A and B. Let's substitute this back into our inequality. And we arrived at a more general form of the uncertainty relation, known as the Robertson uncertainty relation. This was published by Howard P. Robertson in 1929. Incidentally, this is the same guy in the famous Robertson-Walker metric in cosmology. From this expression, it is even more apparent that complementary observables that do not commute must necessarily have some minimum uncertainties in any state. Let's apply this to position and momentum. And we easily obtain Heisenberg's inequality. This holds for any normalized state and is a fundamental feature of position and momentum, and not simply due to the imperfect way with which the state is measured or prepared. This is often a great source of confusion for uncertainty relations in quantum mechanics. We have reached the end of this video. This concludes Chapter 3, Part 2 of Weinberg's book on quantum mechanics. If you find this video helpful, consider giving it a like and subscribe to this channel so that you can follow along as we go through the whole book. See you next time, and thanks for watching.